Somewhere in the sky right now, there's a patch of light so small you could cover it completely with a single grain of sand held at arm's length. Inside that tiny patch sits a faint red smudge that shouldn't exist. It looks like a mistake. The kind of thing any astronomer would normally throw straight into the trash bin of bad data. Except it's not a mistake. It's real, it's confirmed, and it just forced one of the most respected astrophysics teams on the planet to admit something uncomfortable. They don't fully understand what they're looking at. That faint red smudge has a name now, MOM-Z14. And the story of how it was found and what it might mean is one of the strangest things to come out of space science in years. Subscribe now, because we cover discoveries exactly like this one on a regular basis. Real findings from real published research explained clearly, without unnecessary exaggeration. To understand why this discovery matters, you first need to understand what the universe actually looked like before there was anything worth looking at. Light travels at roughly 300,000 kilometers every second, the fastest anything in the universe can ever move. But space is so mind-bendingly enormous that even at that speed, a single particle of light can spend more time traveling through the universe than planet Earth has even existed. Our universe is about 13.8 billion years old, but for its first few hundred million years, there was nothing to see at all. No galaxies, no stars, no planets, no chemistry. Just a thick, dim fog made almost entirely of hydrogen and helium gas, expanding outward into total darkness. Astronomers call that early stretch the cosmic dark ages, and the name isn't just poetic, it's literally accurate. That primordial fog was so dense that light couldn't travel freely through it at all. Even floating right in the middle of it with your eyes wide open, you would have seen absolutely nothing. Eventually, gravity did what gravity always does. The fog slowly clumped together. Denser pockets of gas pulled in more material, collapsed further, heated up, and eventually ignited into the very first stars. Not gentle, well-behaved stars like our sun, but enormous, violent, and extremely short-lived. Their intense ultraviolet radiation tore through the surrounding neutral hydrogen gas, stripping electrons away from it and burning clear, transparent bubbles into the thick cosmic fog. Those bubbles kept growing, kept merging, and slowly the fog lifted entirely. Scientists call that transition reionization, and the moment it began is what we now call cosmic dawn. Every major telescope pointed toward the deep universe is, in one way or another, trying to catch a glimpse of that exact sunrise. And with every passing year, we push our observations a little closer to that historic moment. Until recently, the record for the most distant confirmed galaxy ever observed belonged to an object called JWST 14-0, another James Webb Space Telescope discovery, with a redshift of 14.32. Redshift is essentially a way of measuring how much the ongoing expansion of space has stretched a light wave during its journey toward us. It functions almost like a built-in clock. A redshift that high told scientists the light they were looking at had left its source when the universe was only about 290 million years old. That already sat right at the edge of what anyone expected to find. Then a research team led by Rohan Naidu at the MIT Kavli Institute for Astrophysics and Space Research went back through imaging data Webb had already collected, specifically hunting for promising candidates other researchers might have overlooked. They found one, an object that showed up clearly at longer infrared wavelengths but essentially vanished at shorter ones. Exactly the signature you'd expect from light so severely redshifted that its entire blue end had been erased. That pattern alone justified dedicating precious telescope time to it. In spring 2025, the team pointed Webb directly at the object and ran its light through NIRSPEC, an instrument that splits incoming light into its individual wavelengths. Essentially the same way a glass prism splits sunlight into a rainbow. That's genuinely how scientists stop guessing and start measuring something with real precision. When the spectrum came back, it confirmed a redshift of 14.44. They named the object MOM-Z14, after the survey that found it, nicknamed Mirage or Miracle. With a single confirmed measurement, the previous distance record was broken. We're now looking at light that departed its galaxy roughly 280 million years after the Big Bang, at a point when the universe had lived through only about 2% of its entire existence so far. Try to actually picture what that means. Imagine compressing the entire history of the universe into a single calendar year. The Big Bang happens in the first instant of January 1st. This galaxy is already shining brightly by around January 7th. The dinosaurs don't show up until the day after Christmas. Every human being who has ever lived fits entirely within the last few minutes before midnight on New Year's Eve. And somehow, we built a machine, launched it roughly 1.5 million kilometers from Earth, and caught a single particle of light from the very first week of January. Here's exactly where the real trouble begins. MOMSI 14 is tiny. Its visible light spans something like 241 light-years across. For comparison, our own Milky Way stretches roughly 100,000 light-years from one edge to the other. We're talking about something literally hundreds of times more compact than the galaxy we live in, closer in overall scale to a single dense star cluster than to what we'd normally call a full galaxy at all. And despite being so small, it's absurdly bright. Pound for pound, this object is putting out far more light than anything that young and that compact has any business producing, according to existing models. Standard formation models say early galaxies at this stage of cosmic history should look dim, messy, and slow to come together. This one instead looks compact, mature, and intensely energetic, almost as if it skipped several stages of normal galactic development entirely. The team's own survey data suggests galaxies this bright are showing up more than 100 times more often at this epoch than pre-Webb models predicted. So what could actually be powering something like this? Scientists have proposed a few possibilities, and each comes with its own uncomfortable implications. One option is that star formation in the extremely early universe was far more efficient than anyone previously assumed, with gas collapsing into new stars unusually quickly and with almost none of the typical inefficiency we see in galaxies forming today. Another is that the very first generation of stars were so massive and so blisteringly hot that a relatively small number of them could genuinely outshine an entire fully formed modern galaxy on their own. Stars potentially hundreds of times more massive than our Sun, burning through their fuel in a fraction of the time and radiating at a ferocity that has no real modern equivalent. A third possibility is that something else entirely is feeding at the center of this object. Potentially an extremely early black hole, already large enough to actively pull in surrounding material and radiate enormous energy as it does, effectively acting as a tiny, ferociously bright engine at the heart of an otherwise unremarkable clump of gas and young stars. Interestingly, when the team looked closely at the spectrum itself, the evidence leaned toward the first two explanations rather than the third. The specific pattern of light didn't show the telltale broad emission lines that usually mark an actively feeding black hole, suggesting most of MOMSI 14's light really is coming from stars rather than an active galactic nucleus. That's a meaningful distinction, because it means the puzzle here isn't a single exotic object skewing the numbers. It's the ordinary seeming process of star formation itself apparently running far hotter and far faster than anyone expected this early in cosmic history. And whichever explanation eventually wins out, every one of them still requires seriously revising something fundamental about how scientists currently believe the early universe worked. But surprisingly, the brightness itself isn't even the strangest detail buried inside this discovery. When researchers examined the full spectrum of light from this galaxy in more detail, they found a specific chemical signature in the surrounding gas, a ratio between nitrogen and carbon that came back unusually, almost impossibly high. Here's why that particular detail matters so much. Heavier chemical elements are never free. The universe was originally born containing almost nothing but hydrogen, helium, and a trace amount of lithium, every other element that exists. The carbon in every living cell, the nitrogen woven into every strand of DNA, even the oxygen you're breathing right now, had to be manufactured inside the cores of stars first, then violently thrown back out into space when those stars eventually died. Building up a meaningfully enriched chemical environment inside any galaxy genuinely takes multiple full generations of stars living, dying, and recycling their material back into their surroundings. At only 280 million years old, there should have barely been enough time for a single full generation of stars to complete that entire life cycle, let alone enough generations stacked on top of each other to explain the kind of chemical imbalance researchers actually detected here. There's a second, equally strange layer buried inside this same finding. That exact nitrogen-rich chemical signature has also been observed somewhere much closer to home, inside globular clusters. Extremely dense, ancient spherical collections containing hundreds of thousands of individual stars, typically found orbiting the outer edges of galaxies, including our own Milky Way. For a long time, these clusters have been treated as relics from somewhere within the first few billion years of cosmic history. If MOMSI 14 is already showing that exact same distinctive chemical fingerprint, it suggests that whatever process actually builds structures like globular clusters may have started kicking into gear almost the moment the early cosmic fog cleared away entirely. That doesn't simply nudge our existing timeline slightly earlier. It genuinely compresses it in a way that's difficult to fully explain. As Naidu himself put it, describing the result, it looks nothing like what the models predicted, which is both challenging and exciting at the same time. At this point, you might reasonably think, fine, this is one strange, unusual object, and outlier discoveries like this happen sometimes in science. Except this isn't just one weird, isolated case sitting off in a corner somewhere. Ever since the James Webb Space Telescope began fully operating in 2022, it has returned some version of this exact same surprising result over and over again. Galaxy after galaxy spotted deep in the early universe keeps turning out too luminous, too developed, too chemically enriched, and too structurally organized for the specific moment in cosmic history we're catching it in. What researchers originally expected to be a small handful of rare exceptions has quietly, steadily turned into something that increasingly looks like the standard result instead. This matters enormously, because our current scientific framework for how large-scale cosmic structure assembles over time isn't something casually sketched on the back of a napkin. It represents decades of careful observation, detailed simulation, and repeated testing, and it has genuinely survived an enormous number of those tests successfully. That framework isn't simply wrong, but it does keep getting surprised, again and again, in this exact same direction. And a scientific model that keeps getting surprised consistently in the same specific direction is a model that almost certainly has some kind of genuine gap hiding inside it somewhere. Maybe dark matter played a far more aggressive role in seeding the earliest cosmic structures than current models have properly accounted for. Maybe the underlying physics governing that very first generation of stars is meaningfully different from anything currently in our existing scientific catalog. Maybe there's some entirely unknown mechanism operating during those first 100 million years of cosmic history that scientists simply haven't fully imagined or identified yet. None of that represents science failing at its job. That's actually science doing precisely what it's supposed to do, running directly into a genuine wall of contradictory evidence and refusing to look away from it. Researchers involved in this discovery have already said publicly that Webb appears fully capable of pushing this cosmic frontier back even further, potentially reaching redshifts considered completely unimaginable only a few years ago, edging ever closer to the era of the very first stars in the entire universe. There's also a completely separate, genuinely strange anomaly sitting inside Webb's broader deep field data, and researchers are still actively debating whether it might somehow connect to everything we've just discussed. In 2025, Lior Shamir, a computer scientist at Kansas State University, went through Webb's JADE's deep field images and used an automated tool to sort a large sample of spiral galaxies based purely on which direction their spiral arms wind. Essentially, which way each galaxy is spinning. The resulting count came back noticeably lopsided. Out of 263 galaxies with clearly identifiable rotation, roughly 2/3 spun in the same direction, with the remaining third rotating the opposite way. In a universe with no built-in preferred direction or orientation, that number should land close to an even 50/50th split. There's no obvious reason the wider cosmos should have some kind of built-in favorite rotational direction, and this wasn't the first time Shamir had found a pattern like this either. Smaller versions of the same asymmetry had shown up in earlier ground-based surveys too. Shamir himself raised a genuinely wild-sounding possibility to help explain it, one that honestly sounds more like science fiction than a peer-reviewed paper. What if that spinning imbalance is actually a kind of leftover residue from the specific conditions our own universe originally formed inside of? What if, in some very real physical sense, our entire observable universe is sitting inside something like a black hole? Stick with the logic for a moment, because it's genuinely more coherent as a hypothesis than it sounds at first. When enough matter collapses together under its own gravity, it eventually forms an event horizon, a boundary that not even light can climb back out from once it crosses over. What actually happens beyond that boundary remains genuinely unknown territory. Our current mathematics simply hands us an undefined infinity and stops being useful at that exact point. A concept called black hole cosmology, explored by physicists including Nikodem Poplawski, takes that specific gap in our understanding and offers one possible way of filling it in. What if the interior of a black hole isn't a dead end at all, but a separate region of space that continues expanding on its own? What if everything we currently call our observable universe is simply what the interior of a black hole looks like from the inside? Connect that back to the very beginning of everything. Our standard scientific account already describes the universe as having started from a singularity, an infinitely dense single point, which happens to be the exact same term scientists use to describe the theoretical center of any black hole. Under this interpretation, the Big Bang wasn't necessarily an explosive eruption into empty surrounding space. It may instead represent the far side of a gravitational collapse that happened somewhere else entirely, inside some larger parent universe, at a moment when enough matter fell together and sealed itself off behind its own event horizon. Under that framework, every black hole in our own universe today would, in principle, be doing the exact same thing right now, quietly sealing off a pocket of collapsing matter that, from the inside, might eventually look like its own separate, expanding universe, complete with its own galaxies, its own stars, and eventually its own scientists looking up and wondering where they came from. It's the kind of idea that sounds almost too neat to be real, which is exactly why most cosmologists treat it as a genuinely fringe hypothesis rather than a serious rival to the standard Big Bang model. But a preferred rotational axis, showing up in real observational data, however it's ultimately explained, is not nothing. It's the kind of small, strange, hard-to-explain signal that has historically been worth taking seriously in the history of physics, if only because a few of those signals have eventually turned out to point toward something genuinely new. To be genuinely fair and balanced, there's also a much simpler, more grounded explanation available, and intellectual honesty requires putting it clearly on the table too. That spinning direction imbalance could ultimately turn out to be nothing more than a measurement artifact. Our own Milky Way is itself constantly moving through space, and that motion can subtly brighten certain objects rotating against our direction of travel, while slightly dimming objects rotating along with it, a Doppler effect. If our current estimate of the Milky Way's own rotational motion turns out to be even modestly inaccurate, that alone could introduce a real statistical bias into this kind of data without requiring any deep cosmic mystery to explain it. It's also worth being clear that this specific idea, that our universe might exist inside a black hole, remains a genuinely fringe position in mainstream cosmology, not something the wider scientific community treats as an accepted alternative. Shamir's own paper doesn't claim to have proven it. It simply notes the pattern and lays out the possible explanations, leaving black hole cosmology as one interesting, unproven interpretation among several. That same healthy scientific caution applies just as strongly to MOM-Z14 itself. Small sample sizes can genuinely mislead researchers. Early measurements sometimes get meaningfully revised once additional data comes in. Some of what looks completely impossible today may end up looking fairly unremarkable within a decade or two, once our instruments and our underlying models both continue to improve. Here's the honest, balanced position to actually take away from all of this. Not that the idea of our universe existing inside a black hole has somehow been definitively proven, and also not that the entire concept is simply nonsense to be dismissed outright. The honest position is that we're currently standing in front of several separate, seemingly unrelated pieces of evidence, all quietly pointing in the same uncomfortable general direction at the same time. A galaxy that appears to have formed far too quickly, chemical enrichment that arrived far too early, and a section of sky that seems to display a strangely preferred spinning direction. Roughly 13.5 billion years ago, that faint red smear of light left its home galaxy carrying a genuine scientific question we still can't fully answer today. It's been quietly traveling through the expanding universe ever since, patiently waiting for someone, somewhere, to eventually build a mirror large enough and sensitive enough to finally catch it. We finally did exactly that. And the first thing this discovery told us is that we currently understand considerably less about the early universe than most scientists confidently assumed just a few years ago. So, what do you personally think is really going on out there? Drop your honest thoughts in the comments, and if this kind of deep space mystery genuinely fascinates you, make sure you're subscribed to this channel, because we cover discoveries exactly like this one on a regular basis. Real findings, straight from real published research, explained clearly, without unnecessary exaggeration, because today, once again, the world of space science just got a whole lot stranger.